Get your lunch and then report to fifth period class and eat lunch in your fifth period class as you normally do. So again,
sorry, I'm still at my other school.
Get lunch and then report to your fifth period class. You'll then have fifth period after lunch. Thank you.
Okay. Do I need to give anybody a couple more seconds to grab their notebook paper? Are we all good? I gotta have some interaction, guys. You can chat.
I'm good.
Okay,
Yeah.
Thank you. All right. So, I'm telling you what, every time I try to do a lab, we get stuck remote. And today was a surprise for me because Marion County didn't call off school, but Fairmont State did. So go ahead and you're going to be folding this. I talked about, continental drift in last time. Listen, if you're driving, I promise, don't hurry. I am recording this so you can go back and check on it later. Like if you are driving and you're just listening, please don't worry. And if you're somebody that's sitting at home going, I don't have all the paper that she wants, that's okay. You can go back and do this. But I want to talk to you about the theory of plate tectonics. And let's see here. Sarah, what is the difference between a law and a theory?
Can you hear me?
Yes, I can.
Sorry, I'm having some issues with my computer right now. I can't remember exactly which one, but one of them you need evidence for, right?
Well, they're both going to have evidence, so yes. All right, did Delaney finally get in? I'm sorry, Sarah, I interrupted you. All right, I see Delaney. All right, so both of them require evidence. Jordan, do you want to help her out? Maybe I can help you guys out. So a law.
Yeah.
Go ahead, Jordan.
I think one of them has been like tested repeatedly or something of that. I don't really remember.
That's okay. All right, I'm going to clear this up for you guys. A law, all right, so they both have been tested. They both are based on evidence, but a law is a description, like the law of gravity. It's a description of how gravity works. But a theory is an explanation. And like the theory of plate tectonics. So we went over last time the hypothesis or the idea of Pangea, the idea of continental drift. It was never a theory, and that's because it was rejected. The reason it was rejected basically is because Alfred Wegener couldn't explain how the continents moved. So without that explanation of how it worked, there was just no support for him on his idea of continental drift. Today, we're going to take a look at plate tectonics in a little more detail, but plate tectonics, like I said before, Wegener died before he could ever see his idea come to life. And so the idea of continental drift kind of died off with him in the 1930s. But then we have World War II, and we get some really interesting technology. They developed sonar. And sonar was developed to look for, basically to look for submarines, for enemy submarines that were going to torpedo ships. They also discovered that, hey, this sonar is really good for helping us figure out what is on the floor of the ocean. So that is where we are going to start today. We are going to start with these ideas that brought us to the theory of plate tectonics. And I'm going to take you through the different types of plate boundaries that there are. And you guys are going to draw this. It's not like a really lab like we would do if we were in school, but this is what I want you to do at home with me. So I am going to share a screen, and if anybody sees somebody waiting, or you know of somebody that's waiting, you know, please make sure you just let me know. So I'm going to draw along with you. We'll see how this works. So at the let me get rid of this. At the very top page, I just want you to make a title page. And your title page is going to say, plate boundaries. So the front of your book is going to look like this. And I don't care if you make, like I usually make the book so that it looks that way instead of the way a book usually is. We're going to make it so that it opens up towards you. But your very first page should say plate boundaries. Then you're going to open up your book. And so you have the top page up here. This will be for notes. And then down the bottom page is going to be for drawings. Okay? Is everybody following along? No. I'll assume if anybody needs me to slow down at any point, just holler at me. All right, so I'm going to draw what you guys are going to draw. And remember, our drawings are going to be down here. So the first type of plate boundary are the convergent plate boundaries. Whoops. And so convergent plate boundaries, these are plate boundaries that are coming together. These plates are moving towards each other. To me, I think about the letter C, and I just remember come together. And we are going to discuss three types of, draw three types of convergent boundaries. They're going to be ocean to continent, ocean to ocean, and ocean to continent. So that little colon mark in between just means two. So ocean to continent, ocean to ocean, ocean, whoops, sorry, that should be continent to continent down there. All right. So those will be the three that we're going to draw. So go ahead and flip to the next page. And again, you should have the top up here will be for the notes that I give you, okay? And here's what we're going to draw down here. So the first one I said was ocean to continent. Well, I want you to remember something, that oceanic crust might be thin, but it is more dense. So it's heavier. So this is oceanic crust. I want you to draw that. It is also darker in color. So if you go back through and color these, pick like a dark gray or a black to color around this, because it is dark in color. Because oceanic crust is made mostly of a rock that's called basalt. And it is heavier than than continental plate. So it is going to come together with a big fat continental plate. And remember, even though it's big and fat, it is less dense. So this is a continental plate. And you guys will please excuse me for my drawing skills. We'll just pretend like you know what that is. What do you think these little things are up here? Whoops. Let's see. Erica's driving. I'm not gonna call on her. Rachel, are you here?
Yes, I'm drawing.
Okay. What do you think these things are?
Well, I don't know. Looks like you made smoke coming out of them.
Okay, steam.
Steam. So, oh, I'm trying to think of
Starts with a V.
volcano?
Yes.
Really? Oh, okay.
Yeah, I know, seriously. So, if we look into the ground, you're going to see a magma chamber. If we were to look in there, and these magma chambers are just places, you know, they're just partially melted rock that came from, you know, we have the mantle right here. And so this is partial melting. And if you have partial melting of oceanic crust mixing with continental crust, you get a type of magma that is called andesitic. And that type of magma, which produces these tall, steep volcanoes, is very explosive. So here, that's our ocean. That's our ocean. So this is occurring underneath of the ocean. This right here, this area here is called a subduction zone. A subduction zone happens when you have a dense crust that gets subducted, that sinks below another crust.
I have a question.
Yes.
So the magma in the magma chamber is called that the
Andesitic.
andesitic. So that's what type of magma?
Yes.
Okay.
Because there are lots of different types of magma. We're only going to focus on 3 types in this class. And andesitic is one of them. It comes with an ocean to continent convergent boundary. So this is ocean to continent. And they're coming together. And the ocean is going to go beneath because the oceanic crust is more dense. The continental crust will always go on top of it because it is less dense. All right. And so in your notes on the top page, I want you to provide, can I erase this now?
Yeah, I'm good with it.
Okay. So on the top page under your notes, I want you to put examples of ocean. The examples of ocean to continent, let's see, the Cascade Range, and that's like in, up in Washington State. So the Cascade Mountain Range, it is a volcanic mountain range. So you have volcanic mountains that happen with an ocean to continent convergent boundary. The Andes Mountains. That's also a volcanic mountain range. You have usually andesitic magma. I don't know why there's sometimes that big long line. Andesitic magma, you have a subduction zone. And you have earthquakes. Whoops. So these are all of the things that you have at an ocean to continent convergent boundary. Whoops. So we are going to now turn the page and take a look at, now we're going to take a look at ocean to ocean. Oops, ocean to ocean convergence. All right, so again, this is going to be occurring under the ocean. Oh, go back just for 1 second. One other thing on your ocean to continental convergent plate boundary, there is also going to be a deep ocean trench. For example, the Marianas Trench in the Pacific Ocean, that is the direct result. That is where the Pacific plate is diving under the North American plate. And that's why we have volcanoes, excuse me, up in the upper part of Oregon and all through Washington State. So deep ocean trenches. All right, so let's go back to our drawing. So again, we have oceanic crust. And of course, even though they are going to be the same density, one is going to subduct beneath the other. And so we have a subduction zone. And it's right here. This area is the subduction zone. And again, here is oceanic crust. Notice that it is always going to be thin and it's always going to be dark. And again, the rock type is basalt. And so what do we have here? Well, we are still going to get volcanoes, but they are going to be wider, like a lot wider, and not as dangerous. All right, I ran out of room for that. These are not as dangerous as volcanoes. Now, that being said, volcanoes are always dangerous, but, you know, if they're active. But the kind that you have here, it has basaltic magma. And it is runny and hot. Whoops. Anyway, the basaltic magma is running hot. So instead of those big composite or stratovolcanoes like we saw in the Andes Mountains and in the Cascades, we're going to get something called shield volcanoes. And these are the great big ones. These are the type of volcanoes that you find like in Japan, places like that, the shield volcanoes. Trying to see if I forgot anything. So on your notes at the top of this, hold on just 1 second. Let me stop sharing that screen with you and share something else. I'm trying, hold on guys. All right, can you guys see that?
Yes, we can see it.
Okay, so for your examples, I want you to do Japan, the Aleutian Islands in Alaska. And then like, what do we have? We have, and I know it says violent volcanoes, but I want you to put less violent. That should say less violent. And again, we have earthquakes. So that is our ocean to ocean convergence. All right, I'm going to go back to sharing. Let's go back to sharing our drawings. So our last one for convergence is going to be continent to continent. Now, because the continental crust is so, it's light, so it's not very dense. It will never subduct. There is never a subduction zone with continent to continent. It would be like trying to take a beach ball and push it to the bottom of the pool. What's going to happen when you let go of it, Lacey? Lacey.
It'll float.
Exactly, it's going to pop back up. Same thing with continental crust. It is never going to subduct. So here's what happens. You've got this great big fat continent, like let's say North America, that has collided with another fat continent, let's say Africa. And they just push up against each other and they form these big folded mountains. And they just keep getting higher and higher, except my words got in the way. They form folded mountains, not volcanic mountains. So there's no magma really associated with this because there's no partial melting. And there's no partial melting because there's no subduction. And there's no subduction because continental crust is not dense enough to like sink into the mantle. So we have continental here, we have continental here. And the type of rock, oh, I forgot to tell you the first time, is basically granite. It's filled with something called silicon dioxide, SiO2. So that's basically what granite is made out of. And this will come back to us in a little bit. So this is what happens when two continents hit. And so what are examples? Well, it's nice because we live in one of the examples, the Appalachian Mountains. And the Himalayan Mountains are another example. I feel like I'm not spelling that right. Maybe it's anyway, the Himalayan Mountains those are two examples of continent to continent convergence. So what do you get when that happens? You get deep earthquakes. You also get metamorphosed rock. That means one rock changes into a different type. So if you had sandstone, it would turn into something called, well, sometimes it's quartzite, something like that. If you started out with a rock like limestone, you know, like you might find in your driveway, it would turn into marble. So there's so much pressure and heat when two continents collide that it actually changes what type of rock you get. And like I said, you get folded mountains. All right, so we are ready to move on to our next section. And our next section is going to be, and you can turn your page, divergent boundaries. And divergent boundaries are pull apart zones. I always think about it like this: divergent, they divide. It's also, like I said, it's also called a pull apart zone. This is where new crust forms. All right. So there are only two types. Excuse me. There are only two types of divergent boundaries. And the first one is ocean to ocean. So here we have, again, we have oceanic crust. Whoops, I don't know why that happens.
Were we supposed to?
Pardon me?
Were we supposed to draw the divergent boundaries part?
You can, it's up to you. This is totally for your study enjoyment.
Okay, thank you.
And I use the term enjoyment lightly. All right, so your oceanic crust, one of them is moving that way. One of them is moving this way. So if you have two pieces of crust separating from each other, let me think of who I've got in here. Aaliyah, are you here?
Yep.
All right. What do you think is going to happen in between those two things? If you have two pieces of earth pulling apart, what's going to kind of bubble up through?
Water?
Well, it's underwater, so the water is already there. This is
Magma?
there you go. So we have magma rising up here. And because we are only working with oceanic crust at this point, this type of magma is basaltic. Remember, that is runny and hot. but it is forming new crust. And you also get it piled higher and higher on either side. It actually forms these ridges. Please forgive my drawing ability. In fact, you have one of the largest mountain chains on Earth. I should say ridge chain, because they're not quite like mountains. And because we geologists are so creative, does anybody want to take a stab at what this is called? It's a ridge in the middle of the Atlantic Ocean. And we happen to call it the Mid-Atlantic Ridge. One of the largest mountain chains in the ocean. It runs from, well, the full length of the Atlantic Ocean. Let me share that with you. Not here. Let me find it. There we go. So here is the Mid-Atlantic Ridge. It's something like 5,000 miles long, maybe probably longer now that I'm sitting here thinking about that. But it runs the entire length of the Atlantic Ocean. We didn't even know it was there until, I can't remember the guy's name, discovered it like at first in the 1800s, but it really wasn't looked at until the 1950s. So this isn't something that is, you know, oh, we've always known this. This is what led us to discover seafloor spreading. So what are some examples?
Is that why Iceland is so rocky?
Iceland, yes, it is one of the reasons. It is also the reason that it has volcanoes, is because volcanoes will form at these ridges as well. And so any type of mid-ocean ridge is because of a divergent ocean-to-ocean boundary. The Mid-Atlantic Ridge is probably the most famous and definitely the largest. And what happens at those ridges? You have volcanoes, but like I said before, they're pretty quiet, you know, and by quiet, I just mean with hot runny lava or hot runny magma, it doesn't like explode. They have pretty shallow earthquakes. And of course you get ridge formation. So let's go back to our drawings. That's such a mess. I'm so sorry. All right, so we are going, oh my gosh. Anyway, we're going to go to continent to continent. I'm sorry it's so loud in here, guys. All right, so it's pulling away. And whatever rock was here is now down here. And so you get rift valleys. And let's stop that for a second. So For your examples, there's a rift valley in the Rio Grande. There is also an African rift valley. Actually, the Red Sea is starting to pull apart. So that's one of them. So all of the effects we get are valleys, rift valleys. Again, we get earthquakes. And if there are volcanoes, they're very small and very broad. Another shield volcano.
Go back to the picture quick.
So this is Catholic Schools Week. This is the first day of Catholic Schools Week. And so today is Red, White, and Blue Day. And apparently we're playing music during lunch. So sorry about this. So our last type is going to be transform faults. And these are kind of weird. Because they're kind of going past each other like this. They just slide. So these transform fault boundaries only slide past each other. So let's go to our drawing. And it just basically is like two big slabs of crust. And it doesn't matter. It can be oceanic or it can be continental. And it can be oceanic or continental. And one is sliding this way and one is sliding that way. And so the boundary is right here. This is the boundary. And the most famous one of these is in California. The San Andreas Fault is a large transform fault. So what do you think the most prevalent effect is of a transform fault boundary? Dawson.
I don't really know. I guess a lot of movement above the crust.
Okay, or right on the crust. And so if you live in California, what do you have to watch out for? Delaney, what would you have to watch out for if you live in California?
Maybe earthquakes.
Ding, 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 ding. You get a prize. You get the applause. All right. Yeah. Earthquakes. This is the biggest effect of transform fault boundaries. This is one of the things that happens at any transform fault boundary. And they are the same whether it's ocean to ocean or continent to continent. It doesn't matter. It's the same thing. These are very dangerous earthquakes.
Is this the same type of fault that causes like tsunamis?
That's exactly right. So if these happen, let's say under the ocean, the effect would be a tsunami. And if we were to look at the mid-ocean ridge and we looked at like the plate boundary type, it's going to look like this. It'll look kind of like Harry Potter's head. So, and these little flat spots that I just drew, those are the transform fault boundaries. So you've got the mid-ocean ridge, but along the mid-ocean ridge, and we know that that is a divergent ocean to ocean boundary, but there are earthquake faults there too, or otherwise known as those transform fault boundaries. And so those are the biggest effects that we have, are tsunamis and really dangerous earthquakes. So let me stop sharing that and go back to my slides. And there you can actually see the transform fault boundary in California, the San Andreas Fault. You can stand right on it. I mean, you know, brave people, I guess. But you can stand right on the San Andreas Fault. It's visible. This is, you know, this is what it would look like, a cross section of it. You've got plate movement that goes, like I said, it's like it just slides past. And so what happens is it builds up and it builds up a lot of energy until it finally moves. When it moves, it releases that energy, and that's what the earthquake is. And you guys, this should look familiar to you. These are the plates of the earth. And when I talk about plate boundaries, let me bring this up. Let me go to there we go. When I talk about plate boundaries, the whole plate itself doesn't have to be a continental plate. For example, here's North America. So that part, of course, is the continent, but where it runs into the Caribbean plate, this is oceanic. Okay, so the North American plate, part of it is oceanic, and then over here along the San Andreas Fault, that part is continental. So it's just that it's at the edges of those plates that we get the earthquakes and the volcanoes. When you guys did your earthquake data collection, you should start noticing a huge pattern that those earthquakes fall along the plate boundaries, because that is where almost all of the movement happens on the earth. That is at the plate boundaries. However, we also get pesky little things like Hawaii. Is Hawaii, let's see here. Erica, are you still driving or are you stopped?
I'm stopped now. I'm able to answer.
Okay. Do you know, is Hawaii on the edge of a plate or in the middle of a plate? Or can you think of, is that something, you know, I don't know if I would have not had geology if I would have known this.
Is it in the middle of one?
It is. So that's weird, because in the middle of the plate, you don't expect giant volcanoes. Those should happen at the edges of plates. However, we get things like, I'm going to split this in half. We get things like these big shield volcanoes. Like Hawaii. Or if we are on a continent, we get, this is Old Faithful. Anybody know where Old Faithful is? We get some mud pots. So we got boiling mud. Anybody know where I am trying to draw here? You know, my drawing is so good. I'm shocked.
I mean, I think it's at a national park in, I think, Wyoming, but I don't know which national park.
It is Yellowstone. Thank you very much. So here we are at Yellowstone. And guess what we have underneath of Yellowstone? We have a giant, and we are talking a giant magma chamber. This is the third type of magma that we haven't talked about. It is rhyolitic. Rhyolitic is the most dangerous. I keep running out of room to write. Rhyolitic magma is the most dangerous. And that is because it is the stickiest. And this is not dangerous. But these happen in the middle of plates. So what am I talking about? I'm talking about something called hotspots. No, it's not a place where you can gamble. These hotspots are convection currents that are that are like stuck. So let me clear this and show you. So here we have the Earth, which I'm sure you knew that. And we've got, let's see here. And let's say that this is the crust up here, super thin. We have the mantle. And we've got the heated material rising and then cooling and then sinking. And that is a convection current. Well, most of the time you get these convection currents, you know, they're just minding their own business, moving along the plates, just about a few centimeters at a time throughout the year. But every once in a while, you get some that, let me see here, that will burn a hole. It'll burn a hole right up through the right up through the crust. And they will form either, if it burns through an oceanic plate, it'll form a shield volcano. Whoops. If it burns through a continental plate, it'll form a supervolcano. But these are hot spots, and hot spots do not occur on the edges of plates. Now, scientists aren't sure why these hot spots happen, but the hot spot doesn't keep moving, the crust keeps moving. So, if we take a look, that's not what I want you to see. All right, there it is. So, if you get a hot spot like Hawaii, the magma wells up in the center of the plate due to that convection current. And here's the thing, we don't know why. And so the Pacific plate just keeps on moving, and that magma zone or that magma chamber just keeps burning up through the crust. One of the first islands in that chain of Hawaiian islands is actually Midway Island, which is midway in the middle of the Pacific. And there's another Hawaiian island already forming as we speak. And it's due to that hotspot activity. It's really weird. And so here you have Midway Island, the Emperor Seamount chain. All of those are due to like some hot spots. And that kind of takes us through the idea of plate tectonics and what happens because of the interaction of plates. And truthfully, 50 minutes is a long time to have anybody on a Zoom meeting. I know even without seeing everybody's beautiful faces, I know you guys are tired. Are there any questions about any of this at all?
I don't have a question about that, but I do have a question about last Monday's lab. Do you want us to turn that, like, do you want us to email that to you since we weren't able to turn it in person today?
Is there should be a place for you to turn it in on, hold on Blackboard.
There's a Dropbox.
That's what I
Oh,
thought.
okay. Thank you.
Yeah, that's okay. And I think I'll go through and make sure that those all have labels on those different days. Well, hold on, I just lost you guys. There you are. So, because I know I label it day 1, day 2, day 3, but because we've been in so much Zoom and remote, I'll just make sure that you know where it is. The other thing I wanted to mention to you guys, anytime that we have to be remote, everybody comes at noon. Anytime that we have to be in lab or regular lecture, please make sure you come in your split group. I'm still trying to figure out how I want to do test days. Last year, we just did half the class at noon, half the class at 1, but I'm not sure about that because when we review for your first test, everybody will come in person at noon. Okay, so I know that that can be confusing. This whole semester, you know, this whole COVID thing is confusing, but yes, and I will be posting the PowerPoint that I used today. I will also be posting the lecture because I did record this so that if you need my beautiful drawings, you may have them. But I'll post both the PowerPoints and this recorded lecture. Okay, guys? Other than that, stay safe, stay warm, and I will see everybody on Wednesday. Hopefully, we are all back to normal. We'll go to lab. So my noon group will come at noon and my 1 o'clock group comes at 1 o'clock. Bye, guys.